Okay, 6.5. We're solving problems using quadratic equations. Michael, can you see it there? Can you read?
Should I read it with me?
Yeah.
Yeah, that's fine. In this chapter, you have learned a variety of methods for solving quadratic equations. Graphing, factoring, completing the square, and the quadratic formula. You have applied these skills to solve problems related to the situations that can be modeled by quadratic relations, such as paths of projectiles, shapes of parabolic structures, measurements, problems involving area, and maximizing revenue. Learning to use the most appropriate method in the given situation is an important step in becoming a good problem solver.
Okay, so we're going to use everything that we've learned, specifically these skills here. So graphing, factoring, completing the square, and the quadratic formula. Just as a quick review, what does completing the square tell us? Yeah, Josh.
The vertex.
Yeah, the vertex. Why might the vertex be important? Daniel.
This is the maximum or minimum point?
Yeah, so max. Max or minimum y value. So that's important because depending on what we're graphing, if it's a height versus time, it'll tell us the highest point that that particular object travels. If we're graphing profit, it'll tell us the point at which we're making the most profit. What about factoring? What does this tell us? Why would we factor? Same guys. Selvin, why would we factor something?
To find the x-intercepts.
Good, to find the x-intercepts, and why might that be important?
To find when it's, the y value is 0.
Yeah, and why is that important? You're right. What's an example of why would that be important? Yeah?
Like when something finishes?
Yeah, so the time, usually it's almost always the time when an object hits the ground. Object hits ground. Anyone think of another example? Nicholas?
The distance from when the parabola started.
Yeah, okay, or so distance traveled before it hits the ground. Good. And finally, the last one, quadratic formula. What's that tell us, Jason? Why would we use the quadratic formula? It's a big, long equation.
Oh, to get the x-intercepts.
Right, so it also does the exact same thing as factoring. So why do we have it? Why? If we can already just factor. Steven?
Okay, so you can't actually factor.
Good. So when x-intercepts when not factorable, which we know happens sometimes, or when we're using decimals, right? Okay, so those are the skills that we've learned. Now we're going to put it all together in today's lesson. We're going to figure out when we use them and when we don't. So we have a model of a toy rocket. Here's the path. And this is pretty typical for all objects here. We have -1/2 times gravity constant, t squared, so that's an acceleration constant. You guys will learn that when you take physics next year. And then we have the initial velocity times time plus the height. So this looks very complex right now, as is. There's lots of variables. But what we're going to find out is all of these are given. So 9.8 is given. So we're going to sub that in for G, because it says right here, gravity is 9.8. V0 is the initial vertical velocity in meters per second, and we're told what it is here. So this 60 comes in for V0. And finally, we're told that it's launched from a 3-meter platform, which is the initial height. So this 3 meters goes in for height there. Okay? So then what we end up with is an equation that we're fairly familiar with. Okay? So that's like a regular quadratic that we're used to dealing with just the one unknown t height graphed in relation to h. Yeah?
What about the 1/2?
Oh, sorry, I missed that. So this would be 1/2 of 9.8 is 4.9. Thanks. Okay, I just multiplied the half times 9.8. Okay, so there's our equation. Now we should be able to answer some of these questions. Create a model for the height of a toy rocket launched upwards at 60 from the top of a platform at 30 meters. So there's our model. There's our algebraic equation. How long would the rocket take to fall to Earth, rounded to the nearest hundredth of a second? So they're asking how long. So we're looking for a t value. How long would it take to fall to Earth? So what we need to find then, when it falls to Earth, what's the height going to be? Yeah, Daniel. 0, right? So this is actually asking for the x-intercepts, right? Specifically, it's asking for the second x-intercept. The first one is when it starts, or in this case, if it's launched from a specific height, it's negative, right? So here's our x-intercepts. Here's our parabola, what it's going to look like. And here's our x-intercept. So if we can solve for the x-intercepts, we'll know that the second x-intercept, or the positive x-intercept, will give us the amount of time before it falls to the Earth. So how are you guys going to solve this for the x-intercepts, or t-x-intercepts? What strategy are we going to use? David?
Factoring, or look for the quadratic formula.
Right. Good. So good thought process. He said factoring, which should be the first thing you go to because it's easier if these were whole numbers and if they were factorable. But because they're not, we have to use the quadratic formula. So this, if you haven't already, you need to memorize it. In this case, it's going to be t, because it's our x variable. So there's our formula. And our values then, A would be negative 4.9, B would be 60, and our C value would be 3. We just plug those values in to our quadratic formula down here. Okay? We'll get two values for T. One will be positive and one will be negative. We're going to look only at the positive value because the negative value, negative time, of course, as we know, doesn't exist. Okay, so that'll be our answer. We'll show you that full solution right now. So here's the first one. We just plugged in those variables as I did, 60 and 3 and 9.8, and we developed this formula. That's the one I developed on the other page. Next, we said we let height equal 0, and we use the quadratic formula, and here are our values. This here is plus or minus. Not sure why it didn't print properly, but that should be plus or minus. And we end up with t equals negative 0.05 or t equals 12.3. Any questions about that, how that was used or why it was used? All right. So we know the time that it hits the ground then is after 12.3 seconds. Okay, that's our equation here. This is 12.3 seconds. Okay? We're not going to bother using a graphing calculator. We're going to solve these all ourselves algebraically. Next question says, what is the maximum height of the rocket rounded to the nearest meter? So what are they asking for? Bruce. Maximum height, sorry? Yeah, they're asking for the vertex. When they say the max height, they're actually asking for the vertex. So there's a couple ways we could do this. One is using a formula that we developed. I think it was in the last question of the last chapter, last section. We came up with this formula. Remember I completed the square with all of the variables? The t value of the vertex was negative b over 2a. You guys remember that? You want to see that again? Are you guys okay? All right, no answer. Let's show it again. All right, so we have A. Okay, so here's our completing the square. Because a is negative, then we can see that the vertex we can see that the x component of the vertex is right here. Okay? And because a is negative, we know it's negative b over 2a. So there's our x value of vertex. Okay? So if we know that's our x value of vertex, we can figure it out, which is 6.12, and then we can take this value and plug it back in into the original equation and solve for the height. Okay, so that's what we do here. We take our time of 6.12 and we plug it in for t and solve for our height. It's 187. Any questions about what we did there? So it's a little different. You could have taken this original equation and just completed the square. You could have got the answer that way. They chose to use a formula for the x value of the vertex and then plug that in and solve for the y. I don't know if I would have done it that way. I probably would have just went ahead and completed the square. Okay, remember how we would have done that is you would have factored the 4.9 out. Plus 3 on the end, and then you would have just factored that out and received your y value of the vertex. Yeah, Steven? Sorry? Oh, it's out of the screen? Okay, sorry. Yeah, Josh?
Can you use complete the square for every single equation there is or no?
Yes. Yeah, good question. You can use it for any value of a, b, or c. It's just like the quadratic formula. Okay? You can use it for decimals, any equation. Yeah.
So the mom just teach us to do that way and then
As opposed
skip
to
these other ways.
as opposed to what?
As opposed to the quadratic formula and the factors.
Well, the quadratic formula is different, right? It tells you the x-intercepts. Completing the square tells you the vertex. So they're used for two different reasons. You understand the difference?
Yes.
Okay. One you're solving for the max height, right? You're solving for this point, and one you're solving for these points, right? One argument might be, why don't they just teach us the quadratic formula? Because that always works, and you can get the x-intercepts, and then with those, you can get the vertex. Okay, but they're just giving us different techniques. Depending on what information you're given, certain ways are quicker than others, okay? All right, finally, the last part says, over what time interval is the height of the toy rocket greater than 150? Round to the nearest hundredth of a second. So, this is probably the hardest question so far, the only one that might have been a little different. Who thinks they can tell me how they do this? So we want to know, when is height greater than 150 meters? Who knows what to do here? Okay, Santiago, tell us. Sorry? Yes, good.
And then you bring it back, opposite of whatever sign it had, positive or negative.
Yep.
And incorporate it to C.
Okay, excellent. That's enough. Yeah, exactly right. So you're going to make the height 150. Why? Because that's the point that we're interested in. We want to know the two t values when the height is equal to 150. So what do? We set the height h here, h to 150. And then, as Santiago said, you need to combine that h value now with the c value of 3. So we bring it over to the other side and set everything equal to 0. So 150 becomes negative 150 plus 3 is negative 147. Okay? Now we can go ahead and use the quadratic formula, and solve for t. So we get these two values of t. Any questions there why we did that? So what these two values are going to be now is they're going to be the 2 points. If this is 150 as our height, here's our height versus t, right? There's our 150 line. These 2 points now are going to be on the curve. They're going to be our t values here, 3.4 and 8.9. Those are going to be our two t values when the curve hits 150. So between them will be above 150. Does that make sense? You guys understand that? We put it into the equation. We solve now for those t values when it's 150. So that gives us these 2 points. The height of the toy rocket is greater when we're between those 2 points. And we know that because we know it's a negative a value, so it opens down. Yeah, Daniel.
Sir, will it ever say like when is the height less than 150?
Yeah, it could.
And you would just
The exact same way, and then you would have to realize that you would be going for these points.
so from like whatever 3.4 to 0.
Yes. Yeah, so that's why it's important conceptually you understand what do these points actually mean? Where are they on the graph and what does that represent? It's this point when it hits 150 and this point when it hits 150. Any other questions with that one? All right, next example. Width of a path. We see this quite often, right? We've seen this already in one of our questions, a similar problem to this. Who wants to read? Okay, Noah?
The rectangular park measures 100 meters by 60 meters. Path of constant width is the 8 around the perimeter. The mayor wants to be sure that this path does not reduce the area of grass to more than 10%. What is the maximum allowable width of the path around the nearest 10 feet?
Good. So the hardest part maybe of this question is coming up with this drawing. Okay? It's very difficult for me to teach the process to come up from here to here. The only thing I can say is that it's usually pretty consistent, right? It's usually the same idea where you're assigning one variable to the unknown. Because it tells us it's a constant width, this path all around the garden is going to be x. And these dimensions 60 and 100 are given. Okay? So we have a park, it's 100 by 60. There's our park, and we're making a path around the perimeter. So this is a little bit confusing in the sense that you might have interpreted it with putting your path on the outside here. Okay, if you did that, you would have been in trouble. Wouldn't have got the right answer. Around the perimeter. I'm not sure if that's totally clear that it's inside the perimeter. The mayor wants to be sure that the path does not... the fact that it says it's going to reduce the area, then you have to assume that it's on the inside of that perimeter. Okay? That would be my my reason of why you would draw this path on the inside, because it's saying that it's not to reduce the area of the grass by more than 10%. So the first thing to do is to find out how much the new area can be, is to figure out what the original area is. We know area is length times width. Our length is 100. Our width is 60. So our original area is 6,000. So reduce that by less than 10%. We're going to multiply that area by 0.9. Okay? And the reason why is because that's the maximum amount of area we can be without going greater than 10% reduction. You guys understand that? Okay. So we come up with our diagram here. X is our constant width. Here's our dimensions. And we develop a formula for the area. So it's 100 minus 2x, x and x. So it's this length is going to be here, 100 minus 2x. And this width here is going to be 60 minus 2x. So we developed this formula. 100 minus 2x times 60 minus 2x is equal to 5400 because that's the largest area we can go before reducing more than 10%. Okay, so that's the hardest part right here, developing that formula. In my mind anyways, that seems to be the hardest part. Once you have that, you can expand, simplify, bring all the numbers to one side, and you end up with this formula. That equation there. And again, we use the quadratic formula because it's not factorable by inspection. You can't do it. So we use the quadratic formula, which again, this is plus minus, and we get two values. Now the last step is to check these values to make sure they make sense. So I'm going to take these values and I'm going to look at the original question and plug them in for x here. And what I find is if I plug in x is 78 meters up here, then I won't have any width left. So x can't be 78. Okay? There would be no park at all if this width was 78. You guys see that? So the only answer can be is 1.9. Yep, Daniel.
Sir, I don't get how you got 2x.
2x where?
Where it's 100 minus 2x.
Oh, okay. So here's our length of 100, right, Daniel, from here to here?
Yeah.
Here's an x, and here's an x. So you have to subtract 2x. 1x, 1x. So to get this length here, it's 100 minus x minus another x is 2x.
So it's still
Okay. You see how this width is 100 here, right?
yeah.
You see how this is an x here, right?
Yeah.
And this is another x, right? So this width in here has to be 100 minus 2x.
Oh, okay.
Okay?
Yeah.
All right. Any other questions? That's it. So what is the maximum allowable width of the path rounded to the nearest tenth of a meter? 1.9. All of this is just checking to make sure that those values are possible. All right, next example. This is a big section in this chapter because you do see these types of word problems. You'll see them in the test, you see them all over, and they're giving you all different types. Here, consecutive numbers. The product of two consecutive numbers is 5, 6, 2, 4. What are the numbers? So again, going from here to the quadratic formula that we need to develop is probably the hardest part, and it's difficult to teach. You just really got to think about this. Because each case is different, right? This is different from the path case. So consecutive numbers, as we know, even numbers, they differ by 2. Consecutive numbers differ by 1. Even numbers differ by 2, right? 2, 4, 6. So if we let x represent one of the numbers, then the next number could be x plus 2. Agreed? That works even for negative numbers, right? Negative 10, the next even number you add 2 is negative 8, right? So write and solve the equation to find x. So there's our equation. Why is it this? Because it says the product. So we need to know the product means multiply is equal to this. Okay, so there's our equation. This, arguably, again, is the hardest part of the question. Got to think about it for a while. Once we get that, we can expand and simplify. So we get this equation here, and this is factorable by inspection. We get 74 and 76, so our two values of x are 74 and negative 76.
So if it's consecutive numbers, you should do x plus 2?
If it's consecutive even numbers, yeah,
Oh, if it's consecutive odd numbers.
it would be plus 2, yeah. But if it's just consecutive numbers, it would be plus 1.
If the equation is solvable by inspection, would you take marks off and use the quadratic formula?
No. Okay, the last thing to note is these aren't your consecutive numbers, right? They're obviously not consecutive. 74 and negative 76 are quite far apart, right? These are the two possible values 4x. Remember, your other number is x plus 2. So your consecutive numbers would be 74 and 76, or negative 76 and negative 74. Those are your numbers. Okay? And in this case, the negative numbers are valid, right? We can have negative integers. So either or works, okay? It's not a dimension and it's not time, so you have to consider both cases. So don't say this one is invalid. That's my point. If you say that on a test, that negative 76 is invalid, you're going to get it wrong. Because it's just an integer, it's just a number. There's nothing invalid about that. Last one, right triangle. One leg of a right triangle is 1 centimeter longer than the other leg. The length of the hypotenuse is 9 centimeters greater than that of the shorter leg. So this is the hardest part, is just setting this triangle up. Which I don't think is that hard, right? One leg is x, it's a right triangle, one is 1 greater, and one is 9 greater. The hypotenuse is 9 greater. If we can set up this triangle, then we can use our Pythagorean Theorem, x squared plus x plus 1 squared is equal to x plus 9 squared, which is here. Expand, simplify, we end up with this quadratic here. Factor by inspection, and we get our two values. In this case, we cannot have negative 4 as x because it's a dimension, it's a length. So this becomes a valid. Our only possible answer would be x equals 20, and then you would solve for the other values, 20, 21, 29. Any questions there? All right, the last one I think is a graphing calculator question, so we're going to skip that and go right to the summary. Key concepts. The solution to some problems can be determined by multiplying two linear expressions together, resulting in a quadratic expression. So this is almost always the case, right? When we're dealing with area. Gravitational pull causes projectiles to have a height-time relationship that is quadratic, modeled by this, where g is our acceleration. This is always 9.8 on Earth. Okay. V naught is the initial velocity, which they'll give you, and HO is the initial height, which is also usually given above the ground. Length-area relationships are quadratic since the area is a length times a length measured in square units. So this again is area length times width. And following these steps when determining an algebraic solution. This is important. First, define your variables. So let x represent the unknown. Write an equation to model the situation. Area, for instance, x times x plus 2, or whatever the other width side is. Simplify the equation. So expand, simplify. Solve the equation using an appropriate method. So set everything to one side, equal to 0. Appropriate method would either be factoring by inspection or quadratic formula. Consider the allowable values of the unknown. Reject a solution if necessary, providing an appropriate reason. So if it's a dimension, you can't have a negative value. If it's time, you can't have a negative value. Only if it's appropriate, right? Reject a solution if necessary. If it's just integers, you can have negative values. Provide a concluding statement answering the original question. So, sentence to finish. Any questions? Daniel?
So when you're looking at, like, let's say you have the two x-intercepts.
Yeah.
When you're looking at it in factored form,
Yeah.
and you're looking for the negative one, do you look, like, I don't know how to explain, do you look for, like, the negative one in the equation, or after you would do, like, if it's x minus 20, would that be the negative one, or would it not be, because when that's actually
X minus 20 would be the positive intercept.
Yeah, so, like, x plus 4 you take out.
Yeah, so you would have this equal to 0, right? So x would be negative 4, that's the negative one, and x would be 20.
Yeah, so you wouldn't look at the equation, you'd have to actually look.
Yeah, set them equal to 0. It's tempting to just reverse this sign, but then when you have something like this, it makes more sense to set them equal to 0 and solve. Okay? Any other questions?